Okay, let's see if I can hear myself. Way too close to my camera. Okay. Yep. So I can be heard. So yesterday, if you're joining me for study session, I went through the kind of PyTorch general introduction. We went through why I chose like PyTorch over TensorFlow to learn years ago, and kind of a basic introduction to it. Today, what I'm going to be doing is I have the practical deep learning for coders content in front of me. I've been through this course or whatever course they did years ago, but I need a refresher. And so we're going to be working through um, those 5 lessons without the video, mostly because I don't want to listen to the video again. I feel like my brain is like, I heard that before. I heard that before. And so this is really to refresh. Let's pull up where you can find this book, and I'll put it in the comments. Okay. This is a really great course because it has the code in it. And so all you really need to do is start with it and go from there. And they do now have courses on stable diffusion and everything, so you can get started with I got it started with you can buy the book, which is very highly rated, and or you can just read the book here online. Okay. It is by Fast AI and Rachel Thomas, who built kind of this thing we're going to use to have a great API. And yeah, so what we can do is send this. I feel like the site structure has changed some. Okay, yeah, it has. Let me. That's fine. I'll just post it in the comment. Okay, and so you can click through their notebooks here because they do have notebooks, or you can because they have like the notebooks, or you can do what I did, which is kind of download them and add them to VS Code, mostly because I want to work in an interface I'm familiar with. I don't want to go back and try to figure out Kaggle or Google Colab. So we're going to start with if you click notebook version, that'll get you the notebook. And you can get to all lessons and solutions. Okay. So what we're going to do, and we'll probably go to one of these papers and read it too. To read about their API. I think that'll be interesting to do while we're here. Yes, as well. Okay, so let's start with chapter 1, an introduction. Long introduction, but it has all the book content. Okay, so to run this notebook, I'm just going to get into my virtual environment. And what I'm going to do is go to new terminal and try that again. New terminal. I want to go to command prompt. One second. Oh, I'm not sharing my screen. Let me do that. And share screen. Okay. Let's make this a bit bigger for people to see. Okay. Okay. So this is going to, that book is kind of installing. So what we're going to do is walk through what they call the myths. Takes lots of math, takes lots of data, and expensive computers. And so, no, it doesn't, not these days. Yes, if you're on the research end of data science, like I said yesterday, you wouldn't need a lot of math, but you don't need a lot of images either. So if they have 50. We can get a lot more and get a lot better data, but just to get started, you know. And you don't need expensive computers. More than likely, the computer you're working on is fine, or you can work in a virtual environment, which is typically like $4 or $5 a month, right? Nothing too expensive. And so, applications of deep learning in this section, natural language processing, which we're seeing a lot of that with the chat GPT stuff, computer vision, which isn't just facial recognition that we're seeing pop up at like airports and things like that. I've been looking into like crop usage for like farming, very fascinating stuff. Medicine, anomaly detection, images, medical reports, things like that, biology. A lot of deep learning is used in drug discovery, protein discovery. So I think that's really cool. Image generation, again, a lot of the generative model stuff is now being used. I think we're going to see an advancement in recommendation systems with the generative information and just the advancements of causal inference and kind of how we do that. I don't think we're going to go, I think we're moving away from the classical collaborative filtering book that I learned recommendation on, which I'm saying that, but let me pull it up. Collaborative filtering. Not this. This is not the book. Collaborative. Or it doesn't look like the book. Yeah, that might be the book. It's collaborative something, or hold on. Let's just go to Amazon. Hmm. I need to find the name of that book. I guess people don't use it anymore. It's not going up. All right. No, not collaborative product design. Fascinating. Okay, I need to figure out this book, but I think the contents are oldies but goodies. But I do think the market is moving away from the way I learned it, which is great. Um, Playing games, yeah, we've seen it beat players and robotics. I think that's going to be a little bit longer off. I don't think we have a solution to that. And I do think financial, logistics, text to speech, all of those things are coming or are here in some form, and deep learning has a play to that. So, one deep learning model that you've probably or heard a lot about is going to be your neural networks. And it's cool because it's trying to mimic how we process our neurons through like a computer, and that's kind of our current model for it. I don't know if that's going to stay the model forever. Um, you know, um, because we have to start with what we know, but computers don't think or operate like us, and I don't think we can ever make them. It just doesn't, like, there's so much about our physiology that we don't understand. And so, how does this work? So, in our brain, the dendrites are the input layers, just like our model has an input layer, and it outputs after it hits the nucleus of the calculations, it outputs to the axon terminals, right? Which is kind of cool. And so they've been developing this concept of the artificial neuron, and a lot of people have been writing papers on it for a very long time, some of which I would really think I would enjoy reading, but I haven't had time to get around to, and I don't think most people have ever read it either. So a lot of that is paper references to give you background. Um, this is kind of the approach that is laid out in one of the most pivotal papers, which is we have a set of processing units, we have a state of activation, we have an output function, we have a pattern of how it connects together, which is where I like to think about stuff, how we propagate those patterns, how it activates after that state, how it learns from all of that, and then the environment that it operates on. And that's how we got, GPUs are coming for us to be able to enable us to be able to do a lot of this fancy work. And that is cool. I don't know, I keep saying cool. That's like a word for everything that I like in like AI and machine learning. So again, this is written by Fast AI, and we'll end up using their API, which I think is a really nifty tool because it does cut down a lot of work when you're doing this, and they think of so much that matters. But one thing I do like about Jeremy, he's largely set taught in this area because he only had a bachelor's in like philosophy, but he taught himself to code it and really did. And I'm self-taught mostly as well. I went to school, but like they didn't cover half of what I needed to know to do work. So anyway, I digress. So how do we learn? I think I'm glad that they kind of go over this, and I think what I'll do is kind of summarize it. And actually, they are really big fans of teaching from the top down and not taking you to the weeds of stuff. And in a lot of cases, you won't need to know the weeds unless you go further into research roles. You're going to be more implementing and acting on the principles of what you're learning. They provide a lot of examples, and they try to remove the barriers for that. One of the things I highly recommend that you do is consider, like I said yesterday, I wrote a journal of what I learned, what I needed to learn, what I was working on going forward. So I wouldn't forget, and at the end of the week, I can round up on anything that I'm missing or didn't understand and go from there. So if I were you, I journal what you're doing. I do that pretty much on every project, even when I'm working these days, because it just helps keep track of what you did and what you didn't do. I keep detailed logs because you never know when someone's going to say something wasn't received or you sent it, and it just helps you keep track of stuff. So I would definitely be sure you're tracking that. And it talks, a bit about mindset and what we're going to be doing, which is cool. So now we're going to go to our kind of first model. Now, you can, again, if you don't have a GPU, you can get a GPU from any of the service providers. I can get a list to you. There's Paperspace, there's HyperCloud, there's a bunch of others I can't think off of my name, top of my head, but you can use it. Or again, you can just pull up Google Colab as a notebook and use that. Here, and they start with kind of the basic stuff. Let's see if it installed it to install. Okay. They start with some of the basic stuff. So actually I'm going to go back up and see like this is running. And I might actually have to go use Google Colab, which is a bummer. Hold on, let's see. We'll just go here. See if it gives different instructions. Oh, okay. So there's not a conda installation for Fastbook. I'm not going to make another environment. I don't think it's worth busting this one. Okay, let's see if this guy is correct on how to do the conda installation. Let's try. Okay, give that a second. So while we wait for that to think about working, I'm going to go back down and walk through this before I run stuff. Because we're kind of going to be focused on a lot of the things to do at the end, more of the activities than the notebook. Because I don't think you learn by just rote doing the notebook. Or you definitely don't relearn that way. Okay, so what does this code do? This code is importing from the FastData notebook. It is getting the data from, I'm guessing, the built-in library. And it's creating a function called isCat, and it's going to return uppercase name of that cat. It's going to load the image from name function. So it's going to give the path. This is the path that is loading. It's going to get the images from that path, and it's setting a random seed. I'm not sure what valid percent is, but since I don't know, what I'm going to do is type FastAI valid percent and see what it does. So fast AI docs valid underscore percent. Let's see if it tells me. So I don't think that's the top function. Actually, I'm positive it's not. What's the top function of this? Get image files. Yeah, that's the one I wanted to search. So let's look at control find get image files. There we go. So get image files here. Valid percent. So it's a float. And get function path, list of function names, path, label names, valid percent. It's a random subset of. Okay, so this is getting the validation set. Because there's the validation set is a random subset of valid percent optionally created with seed for reproducibility. So we gave it a seed, it was 42, so it's reproducible. And the validation set is a subset of the percent it pulls. I'm guessing it's pulling a percent of the images. And it's going to create a validation set from a subset of that. I can also view the source data, which, trust me, viewing source data will save your butt sometimes, because if something's running too long and it's a source data that you can write like something differently, it could help. So I'm trying to click. So if you go to source data, because you still don't know what it does, you can view it, the function, how it's written and how it calls. And you can not simply, I shouldn't say that, it's not simple. But here's the default function, right? I can do control find on that to see where it appears anywhere else to make sure I understand what it does. And see if they have additional documentation. But it looks like it's just, or you can search the entire file and view what this is. But it looks like it's just pulling a valid percentage of the images, and it's going to create a validation set from that subset of images. So I'm not going to spend too much time on it. So it's getting isCat as a label function, and we're going to resize it so it fits, I'm assuming, into a certain dimension. Then we're going to get Vision Learner, which I don't know what it does either, but it looks like it's pulling ResNet and it's giving an error rate here. And it's going to start fine tuning. So let's figure out what Vision Learner is too before we go ahead and, so it looks like this is working. Let's go ahead and look up Vision Learner so that we can know what it does before we start writing the code. And again, I'm not writing it down yet. because I'm studying and I'm kind of the person that needs to write it down after. I just highlight what I need to know. But if you're the person that annotates as you go along, then you would want to write down Vision Learner and what it does. That was not on this page, so let's do this. There it is. It's on the side right here. Didn't have to go far. All right, so all the functions necessary to build the learner. So obviously it is a learning, and it is suitable for transfer learning. So it does transfer learning. The most important functions are Vision Learner and UNet Learner, and they help you define a learner using a pre-trained model. So since we're pulling their information, it must be a pre-trained model. So what is it doing? It has these aspects. Let's pull up the code. DLS, ResNet, 34 metrics and error rates. So if we pull this up and let me look again. I have a short memory. It's the function Vision Learner, and we haven't made anything else. So what is the first parameter? Let's see if it tells me. Oh, first is DLS. All right, and then so this is what we have. DLS, the next unnamed one is ARC, which that's for DLS Learner. It's the same thing up here. There we go. Same thing. Learner conveniences, it'll tell you. So if you're a learner model, it'll tell you more if you click further into the documentation. Everything you need. They have optional metrics. You can look at all the metrics available to you, I'm assuming. A metrics name, accumulation. Average loss, value metrics. That's more information on how to do that. And let's go back. So it's just a learner, transfer learn. That's all we really need to know for now. I'm going to go back one more. And let's check. Okay, that's all we need to know. So let's check the status. Okay, I think I accidentally typed it to my command line. I'm going to just load it. Sentence piece. Okay, we're going to see if this will work without it for now. Okay, there we go. No, that's just markup. Silly me. Okay, let's go back. Now that we kind of understand what this is doing, I'm going to run this. And it's going to fine tune. Actually, I know what fine tuning is, but for the sake of argument, fine tuning is like adjusting the hyperparameters of the model. So we're going to just go ahead though and look up fine tune. Yeah. And it's going to run. How does it work? So you know. If I can find it. Oh, that's a tutorial. I might not be able to find it for their definition. Okay, yeah, fine tune the learner. So fine tune, if we look at ours, we pass in all of the default parameters. No, fine tune is one. So that's going to be one epoch. It's going to train one epoch, and it's going to have the rest of these defaults here available. And basically what is automatically set to. And we're going to probably get more into what we changed there as well. Okay, so it's definitely tuning stuff. Tuning stuff. Now, okay, we're going to let that finish going. Now, more information about how this book is written, that doesn't matter. So it's trying to demonstrate what it is. So this is going to pull that image and turn it into a thumbnail, I'm guessing. So again, we can, hold on. Thank you for telling me what it is. RGB pillow image that can show itself and convert to a tensor image. And so it's converting the input of this function, which is image cat, from it's going to create from that. I'm guessing that's built in because I don't remember running anything separate. Oh, no, label function. No, that's isCat. It's not image cat. isCat. Yeah, it looks built in. Okay. Into a thumbnail. Oh, that's not going to run. So let me. Now, if the model's any good, right. Looking at the error rate. First thing that tells you if anything is good or bad. The other thing is we can find any image of a cat or a dog, upload it, and it should be able to predict on the pre-trained model. That's kind of the concept, which is really cool, right? That's kind of what this whole point is. I'm going to keep going because the whole point is I want to get to the questions. For this book, we can't actually click and upload button, so we fake it. Yeah, so it's faking the upload click, and it's creating basically it's telling you that the image is saved on their local computer in an image file. This is that image, and it's going to upload it as a fake upload file. Instead, when it fake loads an upload file, it kind of mimics the printout and gets the probability from the model that's running above, and you're going to predict on the first item, and it's going to say it's a cat. And I'm assuming this, like it says, chapter 1 cat example. So one of the things I wanted to say for anyone who's kind of new to data science in general is you kind of have to have a specialty. And they don't talk about that in school. They kind of teach you a bunch of different things and they won't tell you. But people specialize in deep learning or machine learning or general data science in an industry like marketing or transportation or any of that. You typically specialize. And that's just because that knowledge, that specialization helps you do certain tasks really well. And so I don't recommend focusing on both if you want to do one over the other. It just really depends on what that job description says, one. But also, I typically don't see jobs that want deep learning talking about standard machine learning models and practices in theory. Same with general data science, which is more statistics, kind of metrics based, like that. So, inputs, program results. That's how neural networks work. Now, we're going to talk about weights, so I'm going to slow down and go through this part. So we know just by how we look at something if it's like what that object is. Like we know that's a cat and we know that's a dog. We don't have to think about it because we were taught in our language what that was. That doesn't really work for computers, right? So computers have to be taught in a mathematical language, which they speak, if that's a cat or if that's a dog. And it does that by trying to understand the pixels and characteristics and how they form together to do it. And that takes a lot more work than it takes for us to do. But it does it a lot faster than us if we have a lot of stuff at scale. So there are a lot of concepts embedded in this statement. So the statement says, suppose we arrange for some automatic means of testing the effectiveness of any current weight assignment in terms of actual performance and provide a mechanism for altering the weight assignment so as to maximize the performance. We need to not go into the details of the procedure to see that it could be made entirely automatic and to see the machine so performed would learn from its experience. So one a concept that they bring out is the idea of weight assignment. Two, the fact that every weight assignment has some actual performance. Three, the requirement that there be an automatic means of testing that performance. And four, the need for a mechanism for improving that gets the results. That is kind of what it's talking about here. And the one thing I always hate about math that you might not hate about math is everyone calls things a tons of different names, and I don't know what you're talking about. Weights are another way to say parameters. So what are the parameters you're providing to the model so it can do its thing with the help of the inputs, or the inputs with the help of the parameters, right? And so weights are parameters, and there are a specific types of weights associated with the parameters. And so it really all just gets confusing to keep into your head, which is why I have to refresh because all of my vocabulary is off. So let's say one of the reasons why deep learning works is because it's giving a lot of different, measuring a lot of performances, and it's learning off of the different performances, and that's how it's able to learn. Basically, a deep learning model that beats a chess player is basically playing hundreds of games of chess and memorize all of the plays and all the moves possible to happen, and it does the next predicted pattern that it knows. And so but to get that, it had to be trained and taught by, starting with general play, chess books, and then moving into playing other people and then saying, no, this doesn't work this way, or yes, this works that way. It's really fascinating, but that's kind of how it works. And so you have to have that performance aspects to help improve the parameters and kind of really tune the model, right? Okay, so now that you have that, you have this graph, which means you take your inputs, your parameters, / weights, you look at the model, you look at the results, you get your performance, and you update everything all over again. That's kind of the process that you're working through. Okay, so what then specifically is a neural network? And how do I want to read their explanation, and I'll restate it if I think it needs to be restated, or just read it out. I don't know, I just think of neural networks as another algorithm I can use and it does X, Y, and Z. So basically, let's say, yes, it's a machine learning model. It's because people use it. Now that's backwards. I don't know, gradient descent, like gradient boosting models, are not neural networks, but they win everything on Kaggle and they're very powerful performance, right? And so stochastic gradient descents help us find those parameter values, those weight values a lot faster and more automatically. That is the mechanism for helping to improve the neural network, which is basically that type of model. And they're going to dive into that jargon. Yes, jargon, lots of jargon. We measure performance by measuring the loss. That makes sense. Results, predictions. So predictions get the loss, update parameters. Cool stuff. Right, can't be created without data. It doesn't recommend, it only predicts. We're working on the recommends aspect of data. Um, we are going to import their code, and it's going to, we went through a lot of what that is. Let's start here. So one aspect of that item, this part, batch transforms, item transforms that we had when we were resizing it, those transforms are code that they automatically apply. Here, when they're talking about item transform, they apply for each item and they resize it to 224 pixels. And this is applied to a batch of items to do it. So, print it a standard size and so on and so forth. Let's read through this. The pet dataset contains 7,390 pictures of dogs and cats, consisting of 37 different breeds of dogs and cats. Yeah, I guess so. Each image is labeled using its file name. For instance, Great Pyrenees 173 JPEG is the 173rd example of an image of a Great Pyrenees dog in the dataset. Makes sense. The file names start with the uppercase letter if the file is a cat and a lowercase letter otherwise. We have to tell FastAI how to get labels from the file name, which we do by calling from namefunc, which means, the labels are extracted using a function from the file, and passing it to isCat, which returns, checks if it's upper, because if it's upper, it's a cat. That makes sense now. It's like, why are we checking for upper? Makes no sense. This is not a text data set. We're checking the file, the name, checking the labels of the name. Okay, most important parameter here is valid percent 0.2, which tells it to hold 20% of the data and not use it for training. And that's the holdout validation set. The remaining is the training set used to measure the accuracy of the model. So the whole thing is the validation set. Okay, that wasn't clear in the wording of the documentation. Random seed is 42. Makes sense. Will always show the accuracy using only the validation set, never the training set, which is 100% correct. You can't put your training set in your validation set. It ruins everything and makes it, makes people fudge the accuracy, which isn't so great, even though I'm laughing. You don't want to fudge your accuracy, but people do it all the time. And we just don't want it memorizing because all it does is read it over and over again. Now, I'm sure if you've learned anything in machine learning, we want the data to be fit. We don't want it to be overfit, meaning it fluctuates with every single point there. It just won't generalize very well to additional data inputs, which is hard enough already because data drifts, and if data drifts, it's not like you're getting the same information anyway. And like, is it drifting far from fit? Okay. Getting into stuff that isn't in this document, but it turns into a whole thing. So we don't want to do that. So they keep it out. This creates a convolutional neural network, which is there's different types of neural networks. The one that works most, I think, in computer vision is convolutional neural network or recurrent neural networks. It just depends. A lot of the computer vision technologies that we use run on these. So you don't need to debate. It's not just pick the one that currently works and go for it. So ResNet, I didn't know 34 was the number of layers. I guess you learn something new every day. So ResNet 34 is the number of layers in that architecture. And so you can have resonate 18, resonate 50, 101, 152. Those are just the number of layers. The error rate tells you what percent of images in the validation set were classified incorrectly. Yep. And it's kind of what's important when we're trying to classify something. What percent was classified correct? What percent wasn't classified correct? Fine tuning each epoch to fit just those parts of the model necessary to get the new random head to work with your data set and the number of epochs requested when calling the method. Great. Ooh, I kind of want to read this paper. I'm going to click it and just get it to pull up, and we might read it later. How long is it? It's 11 pages, but that's some of those references. We might add that to the list of cool things to read later. Okay, so it creates and moves and transforms in different layers of the images to construct weights for it. Okay. Actually, let me not skip over this because there might be people who know less than I'm understanding, and I want to make sure I don't confuse you. So, this picture is the first layer's weight. So remember, we have, if you're using Resident 34, there's 34 layers. Okay. Each layer in the image is part with like a graph background. It shows the weights, and the larger section at the bottom shows the parts of the training images most strongly match with each of the weights. So this is these weights, and these are the images most strongly matched. So like the circle loopy things, circle loopy things, strange line things, strange line things, thin line things, thin line things. That's how it's picking up and seeing it, right? Weights that represent diagonal, horizontal, and vertical edges of the images, right? As well as very different gradients, which is it picked up on different colors and it picked up on different lines. These are the basic building blocks for machine computer vision. That's 100% correct. And it reconstructs the rate for each of the features, which makes sense. And he looks for edges, looks for repeated lines. And it's really just identifying the textures and the gradients in its own model. And so the same thing here. It's looking for the lines, it's looking for the edges, it's identifying the textures for it. Now, it did another layer. So basically, it is another layer and it gets more into what it's looking at, right, and what it's identifying. And it does another layer, layer 4, layer 5, all of the data. So this article was using AlexNet. Okay, AlexNet only contained 5 layers. That's what it's studying. But you basically do this type of looking at it as many layers as you put into the model. So apparently, image recognizers can tackle more than just images to complete tasks. It can also look at time series if you convert it to an image, which is fascinating. But yeah, you want to make it make sense before you do that. Let's scroll down. So, jargon recap. This is everything you need to study for words. And it's going to go into this to load text documents so that we can segment the objects there. Text, load, text, code text. Oh, code text. Okay. What is this doing? Object detection. So this is talking about object detection, which we've already gotten some of the current standards. So unless you're in the research aspect of these models, you won't be developing new research in the marketplace on this. You can just kind of pull up those packages, but they're going to try to go through some of that object detection basics here. And load that and classify it. batch size. Right. Order matters, run stuff in order. So what I'm going to do, because this is kind of walking you through rerunning that same code with tabular data, text data, is going to try to fine tune again and do that transfer learning from the original model. Since this, I want to assume you understand general understanding of validation, sets versus test sets versus how to run a Jupyter notebook. I'm not going to go over it. I am going to stop and talk a little bit about. So you don't always need 20% in your validation set. It depends on the size of your model. Two, you might need to, like they said, do more than randomly generate your validation, your test sets, because what the data looks like, and if it's like time series, you might need to order it before you do that. You might need to change the representation, and it just needs to match what the output's going to look like. So don't always just randomly split anything. Really understand the underlying data and its distribution, so that you can split it in the appropriate manner in the size that matters as well, because data does change over time. And also, you could have 5 years of data, but you might find out that the past 2 years of data is different from the 3 years before that, and it's missing information, and that turns into a whole thing, even though the time might not necessarily matter. So, so this is a questionnaire. This is kind of what we're going to do. We're not going to do the definitions. I'm not going to worry about definitions. I would, if you're new to this and you haven't really done any deep learning courses, I would set a time this week to go ahead and answer read through it again, answer the definitions on your own time, so it kind of sticks into your head and you can talk about it. So, like, I like the further research, like why a GPU. It's just optimization and time. Considering the large amounts of data we need to train. Okay. And let's go to notebook number 2. Let me make sure this is not running anymore. Okay, I don't think it is. Okay. So from model to production. And honestly, just like the videos we said yesterday, what you make in PyTorch might not end up in production in an actual coding environment. It might need to be written in TensorFlow. It might need to be written in C++. It might need to be written in Go. Like, this is the end-all be-all if you're on a kind of, not a research based on developing these new types of models, but on an implementation team who designs what it needs to look like. And then you have like the data engineers that kind of lift and load. But you might not have a data engineering team. A machine learning engineering team. You might have to do machine learning engineering yourself, especially if you're earlier in your career and you work at a mid-sized to smaller company. Data scientists do not purely do data science. They might do some data engineering. They might do some machine learning engineering. So it's good to know those parts, right? So this is getting more into, did I have the book already? No, they don't. Okay. This is getting more into the ideas behind making great data products, which definitely read that book if you have time. A lot of the knowledge about data science isn't in traditional school textbooks. It's going to be more in those little books you get from an expert that decided to take a year to write a book. And by the time it comes out, it may or may not still be relevant, but it's still going to be better than guessing at it. 100%. Because things move so quickly. So here, they're going to have us download data from Azure. If you want to, go ahead and sign up for this. Again, I'm just going to go through and talk through it before I do it. That's just how I learn. Especially, and if it's something that I know I already know well, I'm not going to stop and do it during this session. But basically, get a free key from Azure and put that key here. If you do need help doing that and you want to work on this later, you're welcome to DM me on LinkedIn. And I think this is streaming to YouTube or Twitter. So DM me, and I'm trying to make sure I can help you get that going. And you could probably Google how to get the key for Bing image search, right? You can also set it in your terminal, but I wouldn't set it in and the reason I wouldn't set it in my command line is most of you guys, if you're like me, I don't really work in my command line that often. I used to when I was starting out, I did a lot of bash commands, but there's a lot of tools that don't require me to do it anymore. So just set it in your environment where you can see it in your Jupyter notebook. Sorry, it's been a long day. It's been a long day. Okay, so they went to Bing and they downloaded tons of grizzly bear pictures. Personally, I think they should have downloaded pictures of pizza. Pizza is a much better visual. Best food ever created. Thank you, Italy. So they're now choosing an image that they're downloading from, right? Yeah, they're looking at one and they're downloading it and they're saving it to their photo, and they get this big old grizzly bear. And set up the pixel thumbnail to 128 by 128, which is what we're seeing here. Very nice and bright picture. They now have trying to classify, I'm guessing, into 3 different types: grizzly, black, and teddy bear. Okay, so this is kind of working with your directory. So one of the things that helps you not have to stop and break code, like this is making a directory. So it's checking if the file you want to save in exists, right? Is there a path called bears sitting over here? It's not. So if it does not exist, then make it and then do this, right? So it's going to make it, and it's going to set a destination path for each little folder, right, to sort it in. And then it's going to download, right? And then you can get the images from the path that it's saved in. Really cool, really nifty. So here it has bears, black is this image, bears, black is this image. And it'll keep doing that for all of its classifications. Now, oftentimes data is corrupt. So thankfully, they have a built-in function to verify images. It looks like, again, I didn't import anything, so none of my functions work. So here, it's telling you how to look up stuff in Jupyter instead of going to the website. So verify. And it doesn't always work. Hold on. Let me just go ahead and install. So this is telling you what it is. So this is the function. Find images in that file and enumerate them if they don't do what you want, right? That's what it does. So function accepts this, shows the source, and applies that function. So you can also open a window or execute all types of cool stuff that I probably should know about Jupyter Notebook by now. Actually, let me pause and see if any of you guys have questions or if y'all are following along and practicing in your own notebooks just fine while I'm reading through this. So let me know in the, I guess, chat. There should be a chat on each one of the places I'm streaming. Just let me know if you're able to follow along. You've got your notebook running, the code is executing, and you're understanding what it's asking from you. And we'll keep studying together. So I'll actually check my comments. Okay, one thing to be aware of. Right, so models reflect the data you trained on, which is why I think it's hilarious that they decided to train text data off of the Reddit data set for, what was it, Gemini? That was a dumb decision. And I'm going to call it dumb. I'm not going to even sugarcoat it. And it's because of the content that's typically on Reddit. It is not PG, nice and friendly words. It is a lot of people who are anonymous on the internet saying whatever they want to anyone. And it doesn't make for good content to generate models on. And so you can kind of see the disaster that turned into it, because you can trace back to the comments that were made on the Reddit post. It's like executives make decisions that make no sense. And I don't, unless I don't know who they had making that decision. And I know it's not great to be critical of companies. But I do think that was a bad decision. You're trying to say you're keeping up with everyone and show that for your IPO. But in my opinion, it just got you a lot of embarrassment. So there. Now, they're making a healthy skin detector, and they're using a very extreme example to show that it's basically showing only pictures of white women. It's not actually identifying blemishes on the skin, which is also an issue. I mean, if you go back to some of the original image models, they did not classify Black people right. That's one of the biggest things, is they didn't do that. And so I think Facebook had a huge issue with that. They're misclassifying people. These models, they're trying to make them so general that they don't end up helping classifying anything. And so oftentimes in your work, you want to train specifically on data that's more specific. You want to train on a specific data set. We don't have artificial general intelligence. We don't have general things. And they try to train on so much that they don't actually do anything well. And so just really consider what your what the composition of the data that you're training on looks like. And it needs to be diverse enough that it actually hits all of the relevant use cases available. So data loaders, what does it do? It stores whatever data loader objects you pass to it, and makes them available as train and validation sets. So this is a class, right? You can initiate, initialize it, you get items, etc., so forth. They have data blocks. Doesn't tell me what data block does. Just told me what data loader does. Okay, there it is. I see it. For when you don't, a extremely flexible system. Okay, so far we have a number of factory methods for particular combinations of things which are convenient. Okay, and when you don't, you can set your own. Got it. Data blocks. That's convenient. So you can set an image block and a category block, which is what they did. And you have the independent variable. You make prediction that it depends on your target, right? In this case, our images and our dependent are the categories of bears, right? Because the category depends on what the bear looks like. Fun. They get the data files and they randomly split it. So they randomly split the data. Since this is not time-based, I'm guessing they are assuming they have even amount of data, but they're randomly splitting the data that they pulled from Bing into a 20% validation set and an 80% training data set. Right, so independent variable is X, dependent variable is Y. Y is you predict on the dependent variable. Now, parent label. Okay, parent label is just the name of the folder. Nifty. This is resizing. So it gives 64 items at a time, but we can do a max display in a number of rows. Teddy bear, grizzly bear, grizzly bear, grizzly bear. Okay. And it can get, hold on. So resize crops the images. And if you crop it, it can flatten the image. So I wouldn't actually do this. It flattens that image so much to fit in, it squeezes it. Doesn't really show the effective size. Yeah, I wouldn't do that. Squishing it is not a great option. So what are the better options? If you squish and stretch, they end up with unrealistic shapes. It doesn't really teach you anything from the practical shape. It's an unrealistic shape. So we don't want to crop out key parts of information, especially like imagine if this was a health data set and you squished it and it no longer looks like a cancerous tumor. You've just screwed over a patient. So you really have to consider what methods you're using when you're applying these things. And so there's different probably methods from when this book was originally published until now as to handle this. But what do they say now? So right now it says they randomly select part of the image and crop just that part. Okay. Each epoch, which is one complete pass through of our images, we randomly select a different part of that image. Okay. Which means our model can learn to focus and recognize on different features of the image. So it would focus in on this part of the corner, and then the next time this part, the next time this part, so that it's focusing on not taking the whole thing at a time and choking on it. And instead, it bites its pizza one nibble at a time so that it can enjoy the whole thing. And since if it's entirely untrained, it wouldn't know anything. It won't recognize the object rotated by 1 degree. So it just won't do any of that. So we can do that. So it instead of doing resize, we can randomly resize the crop, which is basically we have the teddy bear picture and it zooms in, it zooms out, it takes different focuses on the same image so that it can study each different part. That is a great idea. I knew it did this, but I didn't know that's what it was called. And it gives it a minimum scale, which determines how much to look at. So you can give it smaller bits of the images to learn. I'm assuming it will take longer if you give it smaller bits. They use true to have the same image repeated. Yeah. And now we're looking at data augmentation. There's so many methods of data augmentation for all different types of data. It really gets the types of things you can do. It's hard to all keep into your head. That is for sure. So data augmentation, perspective warping, brightness changes, contrast changes. You could do that with aug transforms. And you can do it in a batch. So warp the image. Make it look like an alien teddy bear. Is what this is doing in batch. What is multi-2? I'm guessing with the multiplier of the transformation, probably. Okay, so now they're going to take a standard image size of 224. They're going to random crop it, and you're going to give it a minimum scale of like how it's zooming on different parts of the picture to 0.5 and do those batch transformations, right? And then you create your learner, you pass it. It's going to be an 18-layer resonant. You look at the error rate, and if you tune it, when they were tuning it, we now get these levels of, after 3 tunes, 0.1, and it took 6 seconds, I'm guessing. No, 6 minutes. Great. Yeah, 6 minutes. I am tired. So classification, interpretation. I love these features of stuff. It automatically does it for me because I hate having to. Now, there's going to be times in your careers where you can't put your particular data into like the standard output to get these beautiful images. And you're just going to have to graph it yourself. It happens. It sucks. But you're going to do it. It's going to be okay. So this kind of gives you a confusion matrix. The actual versus the predicted. So actual 41 were black, 47 grizzly, and 36 teddy bear. Where it matched, right? And they only got these two. It predicted here, and it was not. So it did pretty well. And considering, this is the error rate, it does make sense, right? Now, our loss is talking about the loss function, I believe. The number that is higher if the model is incorrect, especially if it's, confident. So if it's correct but not confident of its correct answer, it would have a higher level of loss. So this is going to start telling us the loss. So this, if I'm reading this correctly, is saying grizzly bear versus black. So it's more confident that this is a grizzly bear. It's more confident this is a black bear. And it believes this is 50 prediction, actual loss probability. Okay, so it predicted it was grizzly. It was actually a black bear, the loss function. So it was a very high loss, and the probability was 74%. This one was 50-50. It predicted actual, everything predicted actually. This predicted it was okay. I feel like my brain is trying to read stuff backwards. So it's correct. So it's lower and it has a higher probability. Yeah, that makes sense. Okay. Whew. My brain and thinking about model development. I haven't had to do this for a few months. I feel like once you get out of it every day, you just, what are we talking about? What are we talking about? So data cleaning is done before we train the model. There's so many methods of that. I do have we're doing a weekly project newsletter, and I think in the one I made earlier this week, it does have like, what do you do if you're working with imbalance? Like, how do you actually, because you clean it and you get stuff out, but that doesn't necessarily help your problem, and so it goes into balancing things and questions around how do you do that to help better choose the right features instead of just wiping stuff out. So all of these questions. So they do, because of that, they have a classified cleaner, which allows you to choose a category, and the training validates to set and view the image with the highest velocity and clean stuff out. So it wants to keep this, it wants to keep that, it wants to keep that. You can drop down and check it yourself when you run the code. And that's just a GUI version for you to clean your stuff. You won't be able to clean it for all of it, but it does work. So using a model for inference, fun times. Okay, so saving your models is one of the things I don't think they teach in schools often, but it is so important because you have a team. They run a model, they go to sleep. They come back and run the same model in the morning. Like, we just wasted compute time. Save your model. Start from where you left off. Is important. And if you're in production, you create that model registry. And in that model registry, what happens is when you save it, if you want to run that current model and get predictions, you can do that. But you can then fail over to a backup model if the output drifts, or if you update it and it can just fail over time. So this concept is very important. It doesn't go away. It just gets more complicated to implement and use when it comes to saving your model. So they're saying that there's usually a save model, function in machine learning. And a lot of models, they have export. All right. And so it exports it into a pickle file. There are different types of files based on whatever language you're working in, and they do not all use a pickle file. I do default to pickles because for the most part, if it's built in Python, you can dump it into a pickle file and you can read the file. But not all of them do that. So just know what you're working with. All right. So then you can you dump it and you load it. I'm pretty sure it's called dump and load in the other languages, but you dump it and you load it, right? And you load it from that path, and you can keep trying to predict new stuff on it and start from where you left off. Now, when you use a model for getting predictions instead of training it, it's called inference. And this is vocabulary that I hate to remember. But if you've already trained it and you're trying to predict on that trained model, it's inference, right? We're trying to infer from what we already did. And it predicts that new picture from that. So good. So this section is talking about how to create a web app from your model. You can do widgets. I think now they're Streamlit. They use Voila. You can use Plotly or to make like a web app. There's like a tons of different things. And if you're doing something for research, you need to demonstrate to like the other part of the product team for whatever reason. I do find it very useful to sometimes spin up. I learned to do this in Flask. It's very inconvenient to learn how to do this in Flask. But just spinning up that basic thing to demonstrate like how it might display to them and make sure they're on the same page as to what the output needs to look like and be used for. You're not always going to have a team that's working with them directly, especially if you're on a small team. So you kind of need to have a method of doing that. So again, just depending on where you're working, you are going to be doing a lot of different things as a part of your job. And it's just, the nature of big versus small companies or teams, really, for that matter, if you're working on something that's in development. And so they are walking back through this, and they are displaying the output of predictions and talking about the labeling and getting that out. So it's 100% probability that was a grizzly bear. And they have their little widget button. It's not rendering, that's fine. But on click, they classify it. So they click the button, it classifies it in the model, shows that you know how to do it, and it'll display that output, right? And that's what this section is doing. So I can upload a picture, click it, it classifies it, and it displays the output. That is kind of your basic workflow for a rough and dirty product demo of how models work. And I have done this, not in their Voila thing, but in Flask, and it has worked. You can make it into a real app and you can deploy it. I think oftentimes when you're working on like portfolio projects, you leave it in the code, but actually the code isn't something that is usable to like the hiring manager who knows nothing about machine learning. So it's better to like write up what it does in a short manner, add some images, but it might be useful to put it into a web app so that they can click on it and see the output, because then they're like, oh, that's what it does. And then you'll get, further up to someone that can understand the code. It's all about how you choose to format it for the person that's going to see it first. You got to get past the automated system. Once you get past the automated system, you get past the recruiter. Then So this is really useful for that thing as well. But also, if you're trying to start a startup and need to make demos for your accelerator investment stuff, this can be done for that. So this is this section. You are building a data product. And so this book, I don't think is going to go into what a data product is, but a data product isn't just the model. It deals with all of the pipelines, everything that's going in it that makes the output, how we handle it, how we store it. And it's kind of it's a product, right? It has all different types of pieces to it. And then it has information about the experimentation and things like that. Domain drift, yes. Where the type of data that our model sees changes over time. It happens all the time. Happens all the time. People change. What people upload changes. It drifts. You don't recognize it. It's a pain in the butt. There are now tools to manage this, unlike years ago. So I had a lot of startups spin up just to handle this part of the process and um, monitoring data quality. Such a pain in the butt. I didn't believe because I came in like after, I guess when they were making GitHub, a few years before they started making that. And people used to do that stuff on paper. Like on paper, they had someone who just reconciled all of the code so it could be typed in with all the changes the coders were making in their own environments. I mean, that had to be a pain in the butt. And that was like, people are still working and coding now who had to do that. Like, that is like how fast things go. It's like mind blowing. But these days, a lot of these processes can be monitored with code. But that's like, in my opinion, a completely different discussion on things you need to consider and how you need to work into it. And you might need to do something like that. This is going into blogging for your resume, and I completely agree with them. You need to write on social if you're out looking for a job versus learning for the sake of learning or already employed and just upskilling. People find you. You are always going to have to talk to your findings to someone. You're going to have to write internal documentation. You are not the only one that needs to know what your code does. It's never going to be like that. And you're not going to be of value to the team if you can't tell people what you're doing and what you're working on. So blogging helps build up that skill and also helps you become a more concise verbal communicator as well. So I would answer these questions. We haven't got to the types of questions I want to answer for myself yet because these are kind of definition questions. But if you haven't done this before, I would highly recommend the definitions. Cool. And, you can write a blog post about what you're learning now while we're doing this study sessions. Or you can write a blog post on what you're working at work. But I do agree with them. Everyone needs to write about what they're doing. It'll help so much. Okay. Ethics. Part of me would like to skip the ethics question, but we probably do need to go over it just real quickly. So, key parts of data ethics. So, feedback loops, bias, recourse processes. Your data is always going to be skewed because human input and human thinking is skewed toward wherever the stuff came from. You need to always consider where this data might be used, who is it being used for, what are they doing, and walk through that user process. I always think, well, actually, I was thinking about it earlier today, but it's not really an ethics problem, but do you understand how your data model is going to be used? Do you understand the people who are going to be using it? Like today when I was reading about McDonald's shutting down their AI drive-through because people couldn't use it, part of me wonders, like, were the data scientists or the software developers, not just the UI designers designing the interface out there, looking at how it was being used? Because like they all have different forms of communication. Like I don't communicate like a UX designer. I communicate to them and I try to speak their language, but those are different minds. Sometimes I find that if I am with someone walking through what they need, I can actually make a better solution for them. And so part of me wonders if they did that or they just sent, how far was actual people developing it from the end user and the products, so they could maybe think of something better. Don't know. But it's the same thing when it comes to like ethics of what you're trying to do. Like, what are the checks that you might need? What are the balances you might need? Considerations. Now, with ChatGPT, in my opinion, a lot of this got thrown out the window because they were like, ooh, fast money. And so they're just, like I said, the Reddit example, they just put everything in there and they didn't consider anything. But you really do have to consider it. It'll mess up the brand. It'll mess up the experience for sure. It'll kind of show that you don't care about your customer. And I think a lot of people are asking those questions now. Like, is AI actually useful for me? Is it giving me my privacy? Is it making me think about stuff I shouldn't be thinking about? Is it giving me a skewed vision of the world? Those are questions that people are asking. And I think as we're the ones building this, we need to help them think through those answers as to what might be best for them. What do they need to fight for regulations and privacy, and ensuring that people can't, manipulate them through showing them false information or skewed information that might just be showing part of the story, not the full story. It's a much bigger problem than it used to be. And so this particular notebook goes into different types of biases, different types of issues that you might find. And honestly, we're still figuring this out. I can't say it's been solved. I can't say everything in this notebook works. But it's something that we have to figure out, and it's something that we have to be conscious with. And I think more companies are trying to be responsible, but at the same time, so we are now into the training digit classifier, and they're going to walk through stochastic gradient descent. And what time is it? So 7:30 in about 7 minutes. Excuse me. It's been a long day. I am going to do a quick check to make sure, because I can only see some comments. I'm going to double check that there's no other comments on LinkedIn really quick, so you might hear some feedback as I pull myself up on a different platform. And part of me would like to okay, no comments, cool. Let me check YouTube. I really are get better at using streaming software. It's so funny. I can develop different parts of software, right? I can't really use it well. I don't feel like software is really made with me in mind and how I view and see the world. And I think that is a problem. I do think that is a problem because I just, I don't know, I view and see the world and how I interact with it very differently from a lot of people, and that's okay. So some software I think just doesn't intuit itself to me, Okay. So where are we? We wanted to get through 4 and 5 today. I think we have enough time to do that. So we're going to go under the hood of digit classifiers and looking at the pixels. So basically, we're not training the model on an actual picture or image, right? Because our face, our eyes can actually see the whole image, and it just makes sense to us. Computers are dumb. Computers have to look at every pixel and how the pixels relate to each other and look, convolute, change, flip, chop, and screw to understand what it's looking at, right? And Jan LeCun, I'm pretty sure he's the guy that always argues with Elon Musk on Twitter. It's funny if you don't follow their beef, but he's still in the field working, and they kind of started this computer system architecture, right? But again, these guys have been coding since this stuff had been reconciled on paper. It's kind of amazing. So there's still a lot of hype. I'm not going to even bother reading through all of this, but there's so much hype around deep learning and everything that it can do. And I think we I don't know. The media likes to jump on the hype cycles, so executives like to jump on the hype cycles, and so we don't ever get to do the stuff that matters, and they blame us for stuff not mattering. It's really frustrating. It's really frustrating. It's like, stop jumping on the hype cycle. Create your own AI strategy. I think they're moving to that, like, this is our vision for AI, this is what we do, this is what we don't do. We don't jump on the hype cycle, this is what we're working on. It'll one day get to that. So this is just going to download all of that data for us. It's going to list it, it's going to sort it. It has the folders of 3s and the folders of 7s, so that's where it's kind of picking up those paths. It's going to open the image. It has 3 there. Now, this is going to the PIO package, is the one that we saw earlier, is the most common one that they use, and it's going to basically import that image and going to convert it into a NumPy array. Because again, it can't actually see anything that we can see. Like I can see my setup here, it actually converts it into numbers. Numbers are the language of how the world was built, right? That's what math is. That's why I really like this field, and I kind of want to do like a self-study PhD into like applied mathematics or even pure mathematics just for the kicks. But time in life, um, time in life. Um, I guess self-study and probably not finish for the next 20 years, depending on what rabbit holes I go down. I might do that. I think it's fun. Okay, so it creates a tensor of the image and they turn it into a data frame, and then they kind of have these numbers, right, that show the array, right, how it converted, like the color code. And what is that? Is it RGB colors, right? So the gradients of those colors, right? The color code that it converts into. And it gives it, 6-point font for grayscale. And so I'm guessing black is 255. And it's got it in from 0 to 17 and 0 to 10 here because it's taking a look at a section of the image, right? Yeah. So the entire image is 28 pixels across and 28 pictures down, 784 pictures. And since this is too big, pixels, not pixel, pictures, pixels. This is too big. They cropped it, right? And so this would be 0 to 28 here and 0 to 28 here. I don't know. I'm guessing it's trying to figure out how relatively dark everything is to each other. So it's trying to find where the pixels are located and how dark it is, right? So they're going to get the average pixel values for the group, and it's going to create a tensor to combine those together. So it's all the 7 pixels combined together and all of the 3 tensors combined together for the data set size of each one. This is just a note on list comprehensions. I'm going to assume you know what a list comprehension is if you're watching this. You might not, and if you don't, probably would love to run my kind of intermediate to advanced Python study sessions again, and I might do that if it comes back with popular interest. But there's a lot of ways to iterate over items. The best thing in Python is a list comprehension, and you kind of need to know that it's not a for loop. Though there is a for there, for loop is really considered that the blocks of code. This is a list comprehension. What is it? Python Tricks is a great book that I'm pretty sure is the same name. Let me pull it up. I have a copy. I've had a copy for years. Probably need to get an updated version. But Python Tricks from Will Python is probably the best book with. Oh no, none of this stuff is sponsored, by the way. If I probably should have thought to get like an affiliate link or something, but it's going to explain Pythonic ways to code, and that actually might be one of the reasons why you're not passing actual job interviews is if you're telling them how to do something, but you're writing it as like a C method of doing something in Python. Python has a way of doing it. All of the languages has ways of building the algorithms, building the methods, building functions. And they're going to look at where you're coding and they're going to say, hey, no, they don't even know the basis of working in this language. They kind of learn, but it's not the right method. So I don't want to take in that overhead of training them. And all entry-level people have that overhead. Heck, I'm pretty sure I have, even though I've been doing this, I guess, 12 odd years between data analytics and data science. I have an overhead of learning depending on what field I'm going into. And so that amount of overhead is like, is it going to take this person a month to get up to date, or it's going to take them 9 months to get up to date? That's a cost to the business. Okay, so we are going to, for every pixel position, compute the average over all images of the intensity of that pixel. To do that, we need to combine the images into a single three-dimensional tensor. And the most common way to describe that is a rank 3 tensor. So we're going to often use stack. There's a stack of the individual tensors in the collection of the single tensor. So you have the 7 tensors all put into a kind of a list. And now they're actually stacking them on top of each other. And they're making it divisible by 255, which is the, max pixels for this type of implementation. And you're going to get the shape. So it creates a stack of 3 tensors. Okay. So this is what I don't like about words, because they're pulling up that point again about things being named, things that you don't know they're being named, so you think it's one thing and it's another. So in this case, dimension is sometimes used 2 ways. Consider that we live in a 3-dimensional space, like in a physical object, and that can be described as a three-dimensional vector, right? So X, Y, and Z axis. But in PyTorch, when they talk about the n dimensions, which looks like number of dimensions of v equals 1, it's not 3. Because v is a vector. And so it's one vector of those 3-dimensional arrays, I'm guessing. So that vector, which is a tensor of rank 1, means that only one axis, even if that axis is a length of 3. Math. In other words, sometimes dimension is used for the size of the axis. Space is 3-dimensional. Other times it's used for the rank or the number of axes. So a matrix of 2 dimensions has 2 axes, x, y. And that's how you get confused very easily with very ambiguous terminologies. Oh, goodness. So if we're going to get the stack mean, it's going to look like this. Why is that? Calculate the mean of all images by taking the mean along the dimension 0 of our stack. Because you start counting at 0 because it's a computer. Not because it's a computer, but that's just how they do it, this thing. And you're going to compute the average pixels of the image. Same thing mean for the tensors with the number 7. And it's just really, really blurry still. So we want to measure the distance for the ideal. How would you calculate how similar a particular image is to each of the ideal digits? Remember to step away from this book and jot down ideas. Before moving on, research shows that we call it pain. So I don't know. That's why we were doing this whole thing over again. So I'm going to guess that it's going to, when it's looking at the digits, and it's trying to see if the images match that image, it's going to look at the position of those images. So that's 1. It might look at where it's graying, because I'm assuming where the more gray stuff on the number 3 is going to vary from where the more gray pixels on the number 7 would be. It's going to look at that. Do you guys have suggestions? I'll pause and see if you guys have suggestions, but those are my 2 suggestions. Might be doing math, like the strength of the pixel. It's like mathing 255 to 253 or close within a approximate range. Pixel by pixel, it's not just pixel position, like the weight of the coloring. Because 3 is close to 8, right? So I'm guessing if it had a group of 8, it would have to say, okay, in these positions, are there pixels of these weights or something like that? Great questions. All great questions. Make sure you're jotting down what you think. It might be different from what I think. Because I'm about to scroll down. So it is going to look at the difference of distances. Because math is all about distance. I don't care what it is. It's just distance. It's not really calculations. It's distance from whatever. We can't just add up the differences between the pixels of the image and the ideal digit. Some differences will be positive while others will be negative. That's true. Because it's like, what direction are you counting in? Positive goes this way, negatives go that way. Well, it's not really a negative in the sense of a number. It's just the distance going in the opposite direction where you started counting. And they will cancel out. So it could be too dark in some places and too light in other places, which is very misleading. I completely agree. So to avoid this, there are two main ways that we measure distance in this context. So absolute value, duh. Where's my brain? I know this. It takes the absolute value of those differences so that it is the same no matter if you're going to your left or to your right. Duh. And this is L1 norm. All right. And it's the absolute difference. L1 is absolute difference. It's definitely going to matter tonight. And the mean of the squared differences makes everything positive and then takes the square root. And that's the root mean squared error or error L2 norm. I do totally forget my math. I don't do it enough. When I was working out of data science, I referenced a lot of my stats, but I didn't really need to know that much to do the job every day. So now what it's doing is it's taking the absolute value of the square root and it's looking at the distances so that you can know what the distance to the ideal 3 is from each thing. And so the other thing it's going to do is going to look at the loss function, which is the measure of error, right? And you're going to find this inside of the functional, and it imports f. Okay, so we import else and then we calculate the L1 loss, which is just the absolute value. And then it calculates the mean square root, which is the loss here, which is L2. L1 here. The squared error penalizes big mistakes. That's the same as in other stuff. Given a vector space of V over a field of real complex numbers. Yeah, I remember that crap. And that is a language, so it really is trying to tell you how to describe and write out everything. It took me so long to read that. And we're not going to math this out. It's not important. You do sometimes, if you're developing stuff, need to understand how to get these things into code, but it really doesn't matter at this point. NumPy arrays and PyTorch temperatures are very similar. That'll help you, and they're faster than pure Python. Python is slow. That's why people have to rewrite things in Go or C++. But it does work for design and testing. And most of our libraries are built in Python or built on top of it for good reason, since it's just the language we use. But I think there's a lot of people looking at how can we make it faster. There is this company. I wrote about it, and I can't remember what the name of it was. Okay. I'm going to skip that. Most because this is just showing that it's the same thing. And which is why it's easier to learn. I don't know if we're going to finish all of this today. So we only got the 1 through 4. Let's see. Compute metrics used in broadcasting. So recall that a metric is a number that is calculated based on the predictions in the correct variables. Of course. Calculate our metric over the validation set so we don't overfit. Okay. So it's going to have, it's importing these validation sets, right? And it's getting this out. It's going to calculate that metric. All right. So, and yes, I always check the shape. I print it out. Even if I'm debugging, I make printouts of my shapes for all of my models. Even in production, like print out what it is to make sure that, so I can know if something died in production for some reason. So it has a validation set of 110, and it says a validation set of 128 images that are all 28 by 28. And he's going to write a function to help us choose if it's going to be a 3 or a 7. So what it's going to do here is going to take in two things. It's going to return the distance between them, and if the absolute value within a certain distance, and if that is close to the mean of it once you get it. And that's how they're going to kind of determine if it's actually a 3 or not. Every image of the validation set. Yeah, that's what I said. Okay, so it returned every single distance in the image. And it does about broadcasting. Now, this is one of those language-specific things that we need to understand how it works so that we don't use it incorrectly. So when it tries to do that subtraction calculation, it does it through broadcasting, which expand the tensor with the smaller rank to have the same size as the one with the higher rank. So if it's a smaller tensor that you're looking at, like one image against all of the images, like it says below, it's just going to expand it so that it works together. That makes sense because, I mean, in math, but in math, like you can't multiply something that's kind of the same size. Well, that's a rate. Anyway. So that you can do that math automatically, like the matrix math, because that's what it's doing for you, is the matrix math. A 2 tensor representing a single image so that it can do it for you automatically. That way you don't have to do that matrix math with that because you can't like multiply things of the wrong size together, or it's more complicated to do so. So they put it in the size that it would work in, even though you're uploading it of a certain size. And it'll do that math for you in the back. I like it. Oh, my face is all up in the camera. I need like a camera crew. So the camera doesn't have to be right there when I'm half blind. If you don't see the glasses, I can't see at distances as clear. And the more tired I get, the more I can't see. So let's say calculate the differences. And it doesn't copy it 110 times. It pretends it were a tensor. It doesn't allocate any additional memory. And does the whole calculation in C, or include a crate if you're doing that, and just broadcast the element-wise operations. Yeah, that's what's called element-wise operations. That's why it's efficient. And so if you don't know that it does that, you might try to do something else and it'll ruin your code. Makes sense. Okay. Test of our example case. So it's saying, is that true? One tensor. All right, this is the function. So return the distance of x and the mean and see if it's less than that distance, the mean here. And it's basically saying, is it true or not? This output's a Boolean. So saying that it is true that the distance is less than, when they compare it, the distance that would be here. So 0, 1. True. And then it calculates the accuracy, so we get the mean of both. 1 minus 7, just flip 3 and 3, and divide by 2. So with 91% accurate, with 98%, that is not that. And divided by 2 is 95. Yeah, on both 3s and 7s when it does the calculation. Yeah. So we're getting into stochastic gradient descent. I don't want to start my brain thinking about a different topic. So I think, because I want to end at 8, I don't want to go past 2 hours. So part of me is like, maybe I should go past 2 hours. but we'll stop at 2 hours and start here tomorrow. Um, if you have questions or need help getting your Azure images set up, please feel free to DM me and we can talk about how to make that work. I would love it if you would connect with me if you're not already connected, and just connect with me on LinkedIn or YouTube or Twitter. I think I'm streaming to all three because I clicked all the buttons. And do that. If you're interested in, I think my newsletter, you can find it on my LinkedIn profile. I have one that sends a project every week and one that is just hot takes on AI in the news that is either happening or happened recently, and how to learn how to do those certain things and things you might need to think about as you're building these technologies. So it's fun, it's quirky. I think with the remaining 10 minutes, there's a few papers that would be interesting to read or go through, or at least the abstract. So they brought up, I really want to find that collaborative filtering book. But the two papers that I clicked on is the FastAI Layered API for Deep Learning, which is their paper that they made in, I'm guessing, 2002. Wait, is it 2002 or is it April 2020? That was the last day it was updated. Yeah, maybe that's the day. And so this is that abstract. So it's a deep learning library that provides with high-level components so you don't have to build it. And also, these guys are data scientists, but they're also building software. Like, it's really underrated that you can contribute to open source projects like this, like packages that you're using. And contributing to that connects you with people who are higher in the field than you, who have connections to roles, or just gives you a different skill set on how to implement some of these things. Because I do think the data science field is going more software heavy than scientist based heavy. So you need fewer people who understand the stats of it all and more people who understand how to build the technology and tools. So I digress. So it is GPU optimized, which is great because that's why NVIDIA is making all that money right now. Things are moving to the GPU to make stuff faster and to train all this massive data everyone's collecting on everyone else and quickly. And so fast AI is another layer of extrapolation so that you only need 4 to 5 lines of code, which keeps your code base lean. And it works for a lot of use cases. It might not necessarily work in in production. So that's really cool. You can definitely check out their GitHub, and it goes through their low level, looking at the tensors to the optimizers, the learner blocks, and the applications you can pull, vision, text, tablet, or collab. And it goes to some of the code it looks like in this paper. Really cool. Let me put this in the comment sections for those of you who would like to read it. And pull up LinkedIn, because I don't think it sends my comments to LinkedIn. I don't think it worked. Okay, there we go. There we go. Awesome. I'm going to get myself out of my camera. All the things to think of. Collaborative filtering models with a nearby collab. There's probabilistic matrix factorization approach. Classic matrix factorization. I do think I have this month looking back into Python for linear algebra so I can get back into matrix. I used to love, I did not pass very highly linear algebra, but that's actually one of my favorite classes. I just didn't have the math foundations to see everything I needed to see, but I love doing the computations. High level APIs. Okay, well, I don't want to keep you guys um, any longer. Oh, to do a partial port of Swift, a faster without too Swift. Cool. I don't want to keep you any longer. You are welcome to, um, yeah, uh, message me if you need some help. And you guys have a great evening. And I hope to see you guys tomorrow. That will be day 26. Today is the end of day 27 of the study sessions.